everyone, welcome back to my channel. I'm Miss Merkin and today we are going to be doing a little bit of trig. So today's video is all about using trigonometric functions or ratios to solve for both missing side lengths and missing angle measures on right triangles. So the first thing that I decided to do is just a little refresher or review on the trig ratios themselves for both regular trig functions and inverse trig functions. So we always have to start when we're talking about trig with some kind of angle or reference angle. We'll call that theta. So theta is going to be our reference angle, and based on whichever theta or reference angle you have chosen, you need to determine where your opposite and adjacent legs are in relationship to that angle. So the adjacent leg is the one that is touching your reference angle. So this one right here is the adjacent leg. Okay. Then we have the opposite leg. So it's the other leg on your right triangle that is opposite or not touching your reference angle. Okay. And finally, we have our hypotenuse. The hypotenuse is the longest side on your right triangle, and it is always opposite of that 90-degree angle. So this right here would be our hypotenuse. All right, so all trig functions are functions where we put in our angle, our reference angle to be specific, and we get an output that is a ratio of two sides on your right triangle. So you could do a ratio of the adjacent leg and the opposite leg and the hypotenuse. That is all trig functions really are. And so each specific type of ratio has its own name for a trig function. So we're going to start out with our first trig ratio, which is sine. So we have sine of our reference angle, which we called theta, and sine of theta is equal to our opposite leg, this one right here, over our hypotenuse. All right, we also have cosine of our reference angle. Cosine is the length of our adjacent leg over our hypotenuse. So in other words, adjacent over hypotenuse. And finally, we have tangent. And so tangent of theta is going to be our opposite over adjacent. So we also have trig ratios that are reciprocal of these. I am not going to cover those in this video, but I have covered them in a previous trig video, and I'll link them in the cards somewhere up here for you guys. So next, what I need to cover, because this video is about finding missing side lengths as well as missing angle measures, we also need to cover inverse of these guys. Now, inverse is just switching your input with your output. So instead of putting in an angle measure and getting out a ratio of sides, I'm going to put in a ratio of sides and get out an angle measure. So if you want, you can pause here. If you want to copy these down, this might be a good time. I'm going to erase these so that I can now write the inverse of each of these trig functions. Okay, so we have the inverse of each of those. So inverse sign, you write like this with a little -1 at the top. So instead of putting in theta, which is my angle measure, I'm going to put in the ratio of sides that corresponds with sine. So sine is opposite over hypotenuse. So it's going to be the inverse sine of opposite leg over my hypotenuse Oh, I did that in purple. Let me keep this consistent for you guys. And for that, I'm going to get out theta. Okay, I'm going to just write out inverse cosine and inverse tangent and then fill in what goes in their inputs and then what their output is. So cosine or inverse cosine and inverse tangent. Okay. So inverse cosine, our ratio for cosine is adjacent over hypotenuse. So I have adjacent over my hypotenuse. And that's going to equal theta. And finally, inverse tangent, I'm going to put in, tangent was opposite over adjacent, so I'm going to put my opposite side length over my adjacent side length, and that's going to get me my angle. Okay, so now that we did a little bit of refreshing on some of these trig ratios and their inverses, we are going to do two example problems. One problem is going to be where we're going to solve for a missing side length on a right triangle using trig, and the other one is going to be a problem where we're going to be given some side lengths, but we're going to have to solve for an angle. Okay, so here's our first example. I am given a right triangle, and on this right triangle, I only know one of the side lengths, and I know one of the angle measures besides this 90 degrees. Now, you could also solve for this angle measure, but in this problem, it's just asking for x and y, and we actually don't need it in order to set up our trig ratios to solve for x and y. So, first, what we're going to do is let's solve for x. Now I'm given this side length right here, and this is actually touching my 35-degree angle, and it is adjacent to the 90-degree angle as well. So this is actually our adjacent leg that we're given. Now over here is what we're trying to solve for. This is a leg and it's opposite of our reference angle, so this is the opposite leg. So what you need to do is set up a trig ratio that uses both the opposite leg and the adjacent leg to solve for x. So that is going to be our tangent trig function. So tangent of theta, which in this case theta is 35 degrees. So tangent of 35 degrees is equal to my opposite leg, which is x, over my adjacent leg, which is 5. So then I have tangent of 35 degrees is equal to x divided by 5. Well, to undo that division, I'm going to do some multiplication. So I'm going to multiply both sides by 5. So then on my left-hand side, I have 5 times tangent of 35 degrees is equal to x. All right, so I've solved for x. This is actually what's called an exact answer. So it's this stage in the game where I'm ready to just punch that in a calculator and get an output. I will create a clip, a little how-to clip as to how to input this into your calculator with a TI-84. So the very first thing you need to do is go to where it says mode, hit the mode button. You need to make sure that your calculator is in degree mode because we're entering in an angle measure that's measured in degrees. So you have to go down all the way until radian degree is highlighted, go over to the right and hit enter on degree, make sure that stays highlighted. Mine was already in degree mode, but yours might have been in radian mode, so you always want to check that first. So then hit second quit to get out of this menu. So then you hit 5, and then it's times. You don't need to hit the times button. So it's 5 times tangent of 35 degrees. And then go ahead and hit enter, and it will give you your answer. So just make sure that you first, before doing any trig and you're using degrees, make sure that your calculator is in degree mode. Everything else is pretty straightforward. Approximation, so it's x is approximately, let me just double check, 3.501, so we'll say about 3.5. Okay, now we need to solve for y. So y is our hypotenuse. So my reference angle is still in the same spot. I'm still given my adjacent leg. You could technically use this length since you've already solved for it, but it's a little easier to use that 5. So we're going to use adjacent and hypotenuse in our trig ratio, which means I need to use cosine. So I have cosine of my reference angle, which is 35 degrees, is equal to adjacent leg, which is 5, divided by my hypotenuse, which is y. Now, I have students right here with a problem like this that always get a little mixed up. Now, we have y in our denominator. So even if I were to get rid of this 5 by dividing both sides by 5, I'd still have a 1 over y on my right-hand side. So instead, what I'm going to do is multiply both sides by y to get y out of the denominator. So then I have y times cosine of 35 degrees is equal to 5. Now to solve for y, I can divide both sides by cosine of 35. So I'm going to go ahead and do that. So y equals 5 over cosine of 35 degrees. This is my exact answer. Now I can put this in a calculator and round. So y is approximately, and once again I've already done this, 6.1038. Okay, so we're going to go with 6.1, about 6.1. Now let's just make sure that this makes sense. So remember, your hypotenuse has to be the longest side on your right triangle. We have found that the hypotenuse is about 6.1, which I buy that, right? Because our one leg is 5, the other one's about 3.5. So it kind of fits our diagram. So that's always a good strategy to use once you've solved for these missing side lengths, to kind of go back and make sure that your answer makes sense. All right, so now we're going to move on to our next example that uses inverse trig. Okay, so in this example, it's slightly different because now we are given two side lengths and we are asked to solve for alpha and beta. Alpha and beta are two angles that are on our right triangle and they are unknowns. So for this example, we're going to have to use inverse trig because we're solving for missing angles instead of missing side lengths. So we're given this 5 and 8. Let's start with solving for alpha. So if alpha is my reference angle, then to alpha, 5 right here, this is actually adjacent to alpha, and I'm given my hypotenuse. So I'm going to have to use inverse cosine because that ratio deals with adjacent and it deals with hypotenuse. So I'm going to set this equation up. So I have cosine or inverse cosine of. Now, when it's inverse, we are now putting in the ratio of sides and getting out the angle measure. So the ratio of sides here is adjacent over hypotenuse, so 5 over 8. And that's going to get me my angle, which is alpha. Well, I've already solved for alpha, right? So I've already come up with the exact answer for alpha. Now, let's use our calculator and approximate inverse trig functions on your calculator. Once again, you need to make sure you're in degree mode because you want to get an output that is an angle measure that's in degrees. Since we've been working with degrees, you can see right here that it says degree, so I am good. Now, I'm going to hit second because I'm going to evaluate the inverse cosine of 5/8. So if you notice, once you hit second, you're going to, you hit these buttons, you hit whatever's blue. So with my trig function, sine, cosine, and tangent buttons, it also gives me my inverse sine, inverse cosine, and inverse tangent, but you have to hit second first. So we're doing inverse cosine, notice the little -1 there, and we're doing inverse cosine of 5 over 8, or 5/8. Close your parenthesis and hit enter, and we get approximately 51.3 degrees. All right, so we found alpha, but now we need to find beta. Well, we don't actually need to use trig to find beta. We could, if we wanted to, we could set up another trig ratio where this is our reference angle and we're dealing with opposite and hypotenuse, so we'd use inverse sine, but we don't need to because on a right triangle, these two angles are what we call complementary, and complementary angles add up to 90 degrees. So what you could do is say, well, beta plus alpha equals 90 degrees. Well, I know that alpha in its exact form is equal to the inverse cosine of 5/8, so I can sub that in. I wouldn't sub in your rounded answer because it's not going to be very exact, so I would sub in the exact answer, which is inverse cosine of 5/8 equals 90 degrees. Well, if we subtract the inverse cosine of 5 over 8 from both sides, we get that beta is equal to 90 degrees minus the inverse cosine of 5/8. So that would be our exact answer. But we could punch this in our calculator to get an approximation. We'll round to the nearest tenth just to keep it consistent. So we get about 38.68. Let's go with 38.7 degrees. Okay, so now you have two examples, one which we used regular standard trig, the other we use inverse trig, and that is it for this video. I hope you enjoyed.